Look up at the night sky on any clear evening, and you'll see thousands of points of light scattered across the cosmic canvas. Stars that have been shining for millions, even billions of years, appearing as constant, reliable beacons in our universe. But what if I told you that some of those very stars you're looking at right now are ticking time bombs, destined to explode with such unimaginable violence that they could fundamentally alter or even end life on Earth? Throughout human history, people have witnessed these stellar explosions. Ancient Chinese astronomers called them guest stars, sudden bright lights that appeared where none had been before. Medieval European chroniclers wrote of new stars that blazed so brilliantly they could be seen during daylight. What they were witnessing were supernovae, the explosive deaths of massive stars, events so powerful they can outshine entire galaxies containing hundreds of billions of stars. But here's what those ancient observers didn't know, what we've only recently come to understand through modern astrophysics. These aren't just pretty light shows in the sky. Supernovae are among the most violent energetic events in the known universe, capable of releasing more energy in a few seconds than our Sun will produce in its entire 10 billion year lifetime. And if one were to occur close enough to Earth, the consequences would be absolutely catastrophic. Now, when we talk about stars exploding near Earth, we have to start with the most obvious candidate. The nearest star to our planet, of course, is our own Sunday. It's sitting there just 93 million miles away, a massive nuclear furnace that's been steadily burning for about 4.5 billion years. So, what would happen if our Sun suddenly went supernova? The answer is both terrifying and fascinating. If you were standing on Earth when our Sun exploded, and somehow managed to look directly at it, you would be witnessing something so bright, so intensely luminous, that it defies human comprehension. To put this in perspective, imagine holding a hydrogen bomb, one of the most powerful weapons ever created by humanity, right up to your eyeball and detonating it. That explosion, happening literally inches from your face, would still be 1 billion times less bright than watching the Sun go supernova from Earth. Think about that for a moment. 1 billion times less bright. We're talking about an explosion so luminous that it makes our most devastating weapons look like flickering candles in comparison. The energy release is so enormous that it challenges our ability to even conceptualize it. But that's just the beginning of what a nearby supernova would mean for our planet. The reality is that a supernova doesn't just produce light. It unleashes a cascade of deadly radiation, high-energy particles, and shock waves that can sterilize planets across vast distances. It strips away atmospheres, bombards surfaces with lethal doses of gamma rays and X-rays, and fundamentally alters the chemistry of space itself. For any life forms unlucky enough to be in the vicinity, a supernova represents nothing less than an extinction-level event. But here's where things get interesting from a scientific perspective. Our Sun, despite being the closest star to Earth, actually can't go supernova. It's not massive enough. Only stars at least 8 to 10 times more massive than our Sun have the gravitational power and nuclear complexity needed to trigger a supernova explosion. Our Sun will eventually die, yes, but it will go out with more of a whimper than a bang, expanding into a red giant and then collapsing into a white dwarf star. So, if our Sun can't explode, what stars can? And more importantly, are there any potential supernova candidates lurking in our cosmic neighborhood, close enough to pose a real threat to life on Earth? The answer to that question takes us on a journey through some of the most extreme objects in our galaxy. We're talking about massive stellar giants, stars so large that if you placed them where our Sun is, they would engulf the orbits of Mars or even Jupiter.
These are stars like Betelgeuse, the red supergiant that forms the shoulder of the constellation, Orion, sitting just over 600 light-years away, or Antares, another red supergiant in the constellation Scorpius. These stellar monsters are already in the final phases of their lives, and when they go, they'll go spectacularly. But distance matters enormously when it comes to supernova threats. 600 light-years might sound far, and it is by human standards, but in cosmic terms, it's practically next door. The question that keeps astronomers up at night is this: how close is too close? At what distance does a supernova transform from an interesting astronomical event into an existential threat to our planet? The current scientific consensus suggests that a supernova would need to occur within about 50 light-years of Earth to cause a major extinction event. Within 100 light-years, we'd still see significant damage to our ozone layer and potential mass extinctions. But even at distances of several hundred light-years, a supernova could have measurable effects on our planet's climate and biology. And here's the unsettling part. There are several known supernova candidates within that danger zone. Wolf-Rayet stars, massive stellar remnants that have blown off their outer layers and are racing toward explosive deaths. Binary star systems where white dwarf stars are stealing material from their companions, building toward the critical mass needed for a Type Ia supernova. These cosmic time bombs are scattered throughout our local galactic neighborhood, and we don't always know when they might detonate. The story of supernovae and their potential impact on Earth is also the story of life itself. These stellar explosions aren't just agents of destruction. They're also the cosmic forges that create and distribute the heavy elements necessary for life. The calcium in your bones, the iron in your blood, the oxygen you breathe, all of these elements were forged in the nuclear furnaces of massive stars and scattered across the galaxy by supernova explosions. In a very real sense, we are made of star stuff, as Carl Sagan famously said. But the same process that created the elements necessary for our existence could also be the process that ends it. It's one of the great ironies of the universe that the phenomena responsible for making life possible could also be responsible for making it extinct. Over the next 2 hours, we're going to explore every aspect of this cosmic threat. We'll dive deep into the physics of stellar explosions, examining exactly how and why massive stars die in such spectacular fashion. We'll look at the different types of supernovae and what makes each one unique. We'll investigate the various ways a nearby supernova could damage or destroy life on Earth, from radiation bombardment to ozone depletion to climate change. We'll also examine the historical evidence. Have supernovae affected Earth in the past? Are there geological and biological signatures of ancient stellar explosions hidden in our planet's rock record? And what can we learn from studying other planets and star systems that have experienced nearby supernovae? Perhaps most importantly, we'll look toward the future. What are the chances that Earth will face a nearby supernova in the coming millions of years? How are astronomers monitoring potential threats? And if we did detect an imminent supernova explosion close to our solar system, what, if anything, could we do about it? This is a story that spans the entire history of the universe, from the first massive stars that exploded billions of years ago to the stellar time bombs that might threaten our descendants millions of years in the future. It's a story of unimaginable violence and breathtaking beauty, of cosmic creation and potential destruction. It's the story of what happens when stars die, and what that means for the fragile bubble of life we call home. Chapter 1. The Anatomy of Stellar Death explores the fundamental physics of how massive stars evolve and die, explaining nuclear fusion processes, stellar mass limits, and the cascade of events that leads to supernova explosions. Covers the difference between stars that become supernovae versus those that don't, using our Sun as a baseline comparison. Stars, those seemingly eternal beacons, aren't immortal. Like everything else in the universe, they have a lifespan, a beginning, a middle, and, yes, an end. But the way a star ends its life is anything but ordinary. In fact, for some stars, it's downright explosive. We're talking, of course, about supernovae. Cosmic detonations so powerful they can briefly outshine entire galaxies. But what exactly causes these stellar fireworks? And why do some stars go out with a bang, while others fade away quietly? To understand the dramatic death of a star, we need to first understand how it lives. Stars, at their core, are giant fusion reactors. They're powered by the relentless process of nuclear fusion, where lighter elements are forced together under immense pressure and temperature to create heavier elements, releasing enormous amounts of energy in the process. Think of it like a controlled, continuous hydrogen bomb. In the heart of a star like our Sun, hydrogen atoms are fused to create helium, releasing the energy that bathes our planet in light and warmth. This process has been going on in our Sun for roughly 5 billion years, and it's expected to continue for another 5 billion years. But what happens when the hydrogen fuel starts to run out? This is where things get interesting, and where the fate of a star diverges depending on its mass. Our Sun, for example, is a relatively small star. When it exhausts its hydrogen fuel, it won't have enough mass to fuse heavier elements like carbon. Instead, the core will contract and heat up, causing the outer layers of the star to expand dramatically. Our Sun will become a red giant, engulfing Mercury, Venus, and possibly even Earth in the process. Eventually, the outer layers of the red giant will drift away, forming a beautiful planetary nebula, a glowing shell of gas surrounding the star's core. The core itself will then cool and shrink into a white dwarf, a dense, Earth-sized remnant that slowly fades away over trillions of years. A peaceful, if somewhat anticlimactic, end. But what about stars much more massive than our Sun? Stars with 8 times, 20 times, even 100 times more mass. These behemoths of the cosmos live fast and die hard. Because of their immense gravity, massive stars can fuse heavier and heavier elements in their cores. After hydrogen, they fuse helium into carbon, then carbon into oxygen, and so on, all the way up to iron. Each fusion stage releases energy, keeping the star stable and preventing it from collapsing under its own gravity. However, there's a crucial difference when it comes to iron. Fusing iron doesn't release energy, energy. It's like trying to burn ash. The star's core becomes a dead end, a growing sphere of iron that can no longer support the star's immense weight. This is where the supernova countdown begins. As the iron core grows, it becomes increasingly unstable. Electrons are forced into the iron nuclei, converting protons into neutrons and releasing a flood of neutrinos, nearly massless particles that stream out of the star at almost the speed of light. The core collapses in on itself with unimaginable speed and force. In a fraction of a second, the core shrinks from the size of Earth to a sphere only a few miles across. The density becomes so extreme that protons and electrons combine to form a giant atomic nucleus made almost entirely of neutrons. This is a neutron star, one of the densest objects in the universe. But the collapse doesn't stop there. The infalling outer layers of the star slam into the incredibly dense neutron core, creating a shockwave that rebounds outwards. This shockwave, combined with the immense flux of neutrinos, tears the star apart in a cataclysmic explosion, a supernova. The energy released in a supernova is staggering. In a matter of weeks, a supernova can emit more energy than our Sun will emit in its entire 10 billion year lifetime. The explosion blasts the star's outer layers into space at speeds of thousands of kilometers per second, enriching the surrounding interstellar medium with heavy elements forged in the star's core. These heavy elements, scattered across the cosmos by supernovae, are the building blocks of new stars, planets, and even life itself. You, me, everything around us is made of stardust, the remnants of ancient stellar explosions. In a very real sense, we are all children of supernovae. So, to recap, small stars like our Sun gently fade away, becoming white dwarfs. Massive stars, on the other hand, meet a much more dramatic end, collapsing and exploding as supernovae, leaving behind either a neutron star or, if the star is massive enough, a black hole. But not all supernovae are created equal. There are different types of these cosmic bombs, each with its own unique mechanism and signature. And some of these types are far more dangerous than others. We've talked about core collapse supernovae, but there's another type that involves white dwarfs in binary systems. And that's where things get even more interesting and potentially much scarier. We've established the basics of stellar death. We've seen how stars like our Sun quietly fade away, and how massive stars explode in spectacular supernovae. But what about those other types of supernovae? The ones that involve white dwarfs in binary systems? How do they work, And why are they so dangerous? Well, that's exactly what we'll be diving into in the next chapter. Types of cosmic bombs. Get ready to explore the different classifications of supernovae, from type Ia to type 2, and discover the distinct mechanisms behind each one. You'll learn why each type poses a different level of threat to nearby planetary systems. It's a cosmic minefield out there, and you need to know what to look for. Chapter 2. Types of cosmic bombs. Detailed examination of different supernova classifications, including type Ia, type 2, and other variants. Explains the distinct mechanisms behind each type, from white dwarf explosions to core collapse events, and why each poses different levels of threat to nearby planetary systems. Not all stellar explosions are created equal. While they all represent the cataclysmic end of a star's life, the mechanisms behind these cosmic fireworks and the threats they pose vary wildly. So, let's delve into the diverse world of supernovae and explore the different types of cosmic bombs lurking in the vast expanse of space. We'll start with one of the most well-understood, and, perhaps ironically, one of the most dangerous types, type Ia supernovae. These explosions don't involve massive, collapsing stars at all. Instead, they are the result of a slow-burning fuse on a stellar remnant called a white dwarf. Imagine a white dwarf, the dense, Earth-sized core left behind after a sun-like star has exhausted its nuclear fuel. These stellar corpses are typically composed of carbon and oxygen, and they're incredibly stable, supported against further collapse by the bizarre quantum mechanical effects of electron degeneracy pressure. But a white dwarf's quiet existence can be disrupted if it happens to be in a binary system, gravitationally bound to another star. Over millions or even billions of years, the white dwarf can siphon off matter from its companion star, slowly accumulating mass. This process is like adding fuel to a dying ember. The white dwarf gets heavier and heavier, its internal pressure rising inexorably. But here's the critical point. There's a limit to how much mass a white dwarf can hold. This limit, known as the Chandrasekhar limit, is about 1/4 times the mass of our Sun. As the white dwarf approaches this limit, something extraordinary happens. The increasing pressure and density reignite nuclear fusion in its core, but not in a controlled, sustainable way like in a normal star. Instead, the fusion process runs away, triggering a runaway thermonuclear reaction. Think of it as a cosmic chain reaction, a runaway inferno ripping through the white dwarf in a matter of seconds. The entire star is consumed in a massive explosion, releasing an absolutely staggering amount of energy. This is a type Ia supernova. It's so bright that it can outshine an entire galaxy for a brief period, making it visible across billions of light-years. The uniformity of type Ia supernovae makes them incredibly valuable to astronomers. Because they all explode with roughly the same intrinsic brightness, they can be used as standard candles to measure distances across the universe. By comparing their apparent brightness to their known intrinsic brightness, astronomers can calculate how far away they are. This technique has been crucial in determining the expansion rate of the universe and the existence of dark energy. But what makes type Ia supernovae so dangerous? It's their sheer power and the unpredictable nature of binary star systems. If a type Ia supernova were to occur too close to our solar system, the consequences could be catastrophic. The intense radiation, particularly gamma rays and X-rays, would bombard Earth, stripping away our atmosphere and potentially triggering a mass extinction event. Now, let's shift our focus to a different class of supernovae, type 2. These are the result of a much more dramatic and arguably more common scenario, the core collapse of a massive star. Imagine a star far more massive than our Sun, perhaps 8 times its mass or even much larger. These stellar giants live fast and die young, burning through their nuclear fuel at an astonishing rate. Throughout their lives, they fuse lighter elements into heavier ones in their cores, progressing from hydrogen to helium, then to carbon, oxygen, silicon, and finally iron. Iron is the end of the line for nuclear fusion in a star's core. Fusing iron requires energy instead of releasing it. So, When a massive star's core is composed primarily of iron, it can no longer support itself against the crushing force of gravity. The core collapses in on itself in a fraction of a second. This implosion is incredibly violent, compressing the core to densities exceeding that of an atomic nucleus. Protons and electrons are forced together to form neutrons, releasing a flood of neutrinos, nearly massless particles that interact very weakly with matter. The collapsing core rebounds violently, sending a shock wave outwards through the star's outer layers. This shock wave, combined with the intense neutrino flux, blasts the star apart in a spectacular explosion. This is a Type II supernova. Unlike Type Ia supernovae, Type II supernovae exhibit a wide range of brightness and other properties, depending on the mass and composition of the progenitor star. They also leave behind a remnant, either a neutron star, an incredibly dense object composed almost entirely of neutrons, or, if the star was massive enough, a black hole, an object with gravity so strong that nothing, not even light, can escape. The threat posed by Type II supernovae is similar to that of Type Ia supernovae: intense radiation, high-energy particles, and powerful shock waves. However, the exact nature of the threat depends on the distance and the specific characteristics of the explosion. But the story doesn't end there. Supernova classification is a complex and evolving field. Astronomers have identified a variety of other supernova types, each with its own unique characteristics and underlying mechanisms. For example, there are Type Ib and Ike supernovae. These are also core collapse supernovae, but they differ from Type II supernovae in that the progenitor stars have lost their outer layers of hydrogen, Type Ib, or both hydrogen and helium, Type Ik, before exploding. This can happen if the star is in a binary system and its outer layers are stripped away by its companion, or if the star has very strong stellar winds that blow away its outer layers. Then there are even rarer types, like superluminous supernovae, which are far brighter than typical supernovae. The mechanisms behind these explosions are still not fully understood, but they may involve the formation of a magnetar, a neutron star with an incredibly strong magnetic field, or the interaction of the supernova ejector with a dense circumstellar medium. Each type of supernova presents a different level of danger depending on its energy output, the distance to the explosion, and the specific wavelengths of radiation emitted. While Type Ia supernovae are generally considered to be more predictable in their brightness, core collapse supernovae can exhibit a wider range of energies and spectral properties. The distance to a supernova is, of course, the most critical factor in determining its threat level. A supernova that occurs hundreds or thousands of light-years away may be a spectacular sight in the night sky, but it poses little direct danger to Earth. However, a supernova that occurs within a few dozen light-years could have devastating consequences. So, how close is too close? What exactly are the lethal effects of a supernova explosion? And what would happen if a supernova were to occur in our cosmic neighborhood? That's precisely what we'll explore in the next chapter, as we venture into the kill zone and quantify the danger distances of these cosmic bombs. You might be surprised by what scientists have discovered. Chapter 3, The Kill Zone, quantifies the danger distances for supernova explosions, exploring the scientific research that determines how close is too close. Examines the various lethal effects including gamma radiation, X-rays, cosmic rays, and shock waves, and how these diminish with distance from the explosion. Imagine standing on a seemingly safe shore, oblivious to the tsunami-gathering force on the horizon. That, in essence, is our situation relative to a nearby supernova. The star perhaps even admire its brilliance without fully grasping the potential for cosmic catastrophe. But how close is too close? What constitutes the kill zone around a stellar explosion? That's precisely what we're going to explore in this chapter. We're not just talking about abstract distances. We're talking about boundaries beyond which the universe becomes actively hostile, capable of sterilizing planets and extinguishing life as we know it. It's a chilling prospect, certainly, but one grounded in solid scientific research. The challenge, of course, is that supernovae are complex events, unleashing a variety of lethal effects, each with its own range and intensity. Figuring out the overall danger zone requires understanding how these individual threats combine and diminish with distance. So, let's start with the most immediate and intense danger: radiation. When a star explodes as a supernova, it releases an absolutely staggering amount of energy, primarily in the form of gamma radiation and X-rays. Think of it as the universe's ultimate flashbulb, but instead of illuminating a room, it's irradiating entire star systems. This initial burst is incredibly intense, capable of delivering a lethal dose of radiation to any unprotected planet within a considerable distance. But how far is that distance exactly? Well, research suggests that a supernova within about 25 to 50 light-years could be devastating. To put that into perspective, the closest star system to our own, Alpha Centauri, is just over 4 light-years away. So, we're talking about a distance range that encompasses a significant number of stars in our galactic neighborhood. The reason this initial burst is so dangerous is that gamma radiation and X-rays are highly energetic forms of electromagnetic radiation. They can penetrate deep into living tissue, damaging DNA and disrupting cellular functions. For a planet like Earth, the immediate effect would be widespread radiation poisoning, potentially leading to mass extinction. But the radiation threat doesn't end there. Following the initial burst, there's a longer-lasting flux of cosmic rays, high-energy particles accelerated to near light speed by the supernova explosion. These particles, mostly protons and atomic nuclei, are like tiny bullets, capable of tearing through matter and causing significant damage. Cosmic rays are particularly insidious because they can travel vast distances, even across interstellar space. While their intensity diminishes with distance, they can still pose a significant threat to planets far beyond the immediate vicinity of the supernova. The Earth's atmosphere and magnetic field offer some protection, but a sufficiently intense flux of cosmic rays could overwhelm these defenses. What you might not realize is that these cosmic rays can also interact with our atmosphere to create secondary particles, further increasing the radiation dose at the surface. It's a complex cascade of events, all stemming from that initial stellar explosion. But the radiation, as terrifying as it is only one piece of the puzzle. Supernovae also generate powerful shock waves, expanding shells of gas and plasma that plow through the surrounding interstellar medium at supersonic speeds. These shock waves are like cosmic bulldozers, sweeping up everything in their path and compressing the surrounding gas and dust. If a supernova shock wave were to encounter a planetary system, the effects could be catastrophic. The shock wave would compress the planet's atmosphere, potentially stripping it away entirely. It could also trigger geological activity, leading to earthquakes and volcanic eruptions. And, of course, the direct impact of the shock wave would be incredibly destructive, pulverizing anything on the surface. Now, the speed and intensity of a supernova shock wave depend on a variety of factors, including the energy of the explosion and the density of the surrounding interstellar medium. But, in general, these shock waves can travel for hundreds, even thousands of light-years, potentially affecting a vast region of space. However, the threat diminishes with distance. The shock wave loses energy as it expands, and its effects become less pronounced. So, while a nearby supernova shock wave could be devastating, a more distant one might only have a minor impact. But even a minor impact could still have significant consequences for a planet's atmosphere and climate. And that brings us to another critical aspect of the supernova kill zone: its indirect effects. Even if a planet isn't directly irradiated or impacted by a shockwave, it can still be affected by the changes that a supernova induces in the surrounding environment. One of the most significant indirect effects is the depletion of the ozone layer. As we mentioned earlier, supernovae release a flood of radiation, including ultraviolet radiation. This radiation can break down ozone molecules in a planet's atmosphere, weakening its ability to shield the surface from harmful UV rays. With a depleted ozone layer, the surface of the planet would be exposed to much higher levels of UV radiation, which can damage DNA, disrupt photosynthesis, and increase the risk of skin cancer. In essence, it would make the planet far less habitable, even if it wasn't directly sterilized by the supernova. But the effects don't stop there. Supernovae can also alter the chemistry of a planet's atmosphere, leading to changes in climate and weather patterns. For example, the increased levels of radiation can trigger chemical reactions that produce smog and acid rain. The shockwave from the supernova can compress the atmosphere, causing drastic weather fluctuations. These changes, in turn, can have profound effects on the planet's ecosystems. Plants and animals may struggle to adapt to the new conditions, leading to widespread extinctions. The balance of nature can be disrupted, potentially leading to a collapse of the entire ecosystem. So, as you can see, the supernova kill zone isn't just about direct radiation or shockwave impacts. It's about the complex interplay of various lethal effects, both direct and indirect, that can combine to make a planet uninhabitable. And figuring out the boundaries of this kill zone requires taking all of these factors into account. But how do scientists actually go about determining these danger distances? What research methods do they use to assess the threat posed by supernovae? Well, it's a combination of theoretical modeling, observational data, and geological evidence. Theoretical models allow scientists to simulate supernova explosions and track the propagation of radiation and shockwaves through space. These models can also be used to assess the impact of supernovae on planetary atmospheres and climates. Observational data comes from telescopes and other instruments that allow scientists to study supernovae in real time. By analyzing the light and radiation emitted by supernovae, scientists can learn about their energy output, composition, and distance. Geological evidence, on the other hand, provides clues about past supernova events that may have affected the Earth. Scientists can look for isotope signatures in rocks and sediments that indicate exposure to high levels of radiation. They can also study the fossil record to see if there's any evidence of mass extinctions that might be linked to supernovae. By combining all of these different lines of evidence, scientists can get a more complete picture of the supernova threat and refine their estimates of the kill zone boundaries. And the more we learn about supernovae, the better we can assess the risk they pose to our planet and our species. Now, let's bring this back to Earth, so to speak. We've talked about the general dangers of supernovae and how scientists determine the kill zone. But what does this mean for our own planet? Are we currently within the kill zone of any known supernova candidates? That's a question that has been the subject of much debate and research. And the answer, as you might expect, is not entirely straightforward. There are several stars in our galactic neighborhood that are considered potential supernova candidates. Some of these stars are relatively close to Earth, while others are more distant. One of the most well-known and closely watched stars is Betelgeuse, a red supergiant located in the constellation Orion. Betelgeuse is nearing the end of its life, and is expected to explode as a supernova sometime in the next million years. Now, Betelgeuse is about 600 light-years away from Earth. That's well outside the immediate kill zone we discussed earlier. However, some scientists believe that a supernova at that distance could still have some noticeable effects on our planet. For example, it could increase the flux of cosmic rays reaching Earth, potentially leading to a slight increase in radiation exposure. There are other, more distant stars that are also considered potential supernova candidates. However, the threat they pose to Earth is generally considered to be lower, due to their greater distance. The truth is, it's difficult to say with certainty whether any particular star will explode as a supernova, and, if so, when. Stellar evolution is a complex process, and there are many factors that can influence a star's fate. But it's important to remember that supernovae are a natural part of the universe, and they have likely played a role in shaping the evolution of life on Earth. So, what have we learned in this chapter? We've explored the concept of the supernova kill zone, examining the various lethal effects that these explosions can unleash. We've seen how radiation, shock waves, and indirect effects can combine to make a planet uninhabitable. And we've discussed how scientists use theoretical models, observational data, and geological evidence to assess the supernova threat. But understanding the kill zone is just the beginning. What about the specific ways in which a supernova could actually damage or destroy life on Earth? What are the most dangerous mechanisms, and how do they compare to known extinction events in our planet's history? That's what we'll be diving into next as we explore the weapons of mass extinction that supernovae wield. Prepare yourself, because the details are even more terrifying than you might imagine. Before we dive deeper into this incredible journey, I'm curious, where in the world are you watching this from? Drop a comment below and let our global community know. And if you're finding this as mind-blowing as I am, hit that like button to help more people discover this story. Chapter 4: Weapons of Mass Extinction. Deep dive into the specific mechanisms by which supernovae could damage or destroy life on Earth, including ozone layer destruction, climate disruption, radiation poisoning, and atmospheric chemistry changes. Compares these effects to known extinction events in Earth's history. Imagine a cosmic shotgun blast. That's essentially what a supernova is. But instead of pellets, this shotgun fires deadly radiation and subatomic particles across interstellar space. What happens when that cosmic buckshot hits a planet teeming with life? The answer, unfortunately, isn't pretty. A nearby supernova could trigger a cascade of catastrophic events, potentially wiping out most, if not all, life on Earth. But how exactly does a star exploding light years away cause such devastation? Let's break down the weapons of mass extinction in a supernova's arsenal. First, consider the ozone layer. This fragile shield in our upper atmosphere protects us from the sun's harmful ultraviolet radiation. A supernova's initial burst of gamma rays and X-rays can rip apart ozone molecules, thinning or even creating a hole in this protective layer. What would that mean for life on Earth? Think of it as opening the floodgates to intense solar radiation. Increased UV exposure can damage DNA, leading to mutations and cancers. It can also disrupt photosynthesis in plants, crippling the base of the food chain. Marine life, especially plankton near the ocean surface, is particularly vulnerable. A significant depletion of the ozone layer could trigger a mass extinction event. But the ozone layer is just the first line of defense. Next up, climate disruption. Supernovae can dramatically alter a planet's climate in several ways. The initial burst of radiation can trigger chemical reactions in the atmosphere, producing nitrogen oxides. These gases can then form a smog-like haze that blocks sunlight, leading to a period of global cooling. However, the long-term effects are more complex. Supernovae also release vast amounts of cosmic rays, high-energy particles that can penetrate deep into the atmosphere. These particles can ionize air molecules, creating more cloud condensation nuclei. More cloud condensation nuclei mean more clouds, which can reflect sunlight back into space, further cooling the planet. However, some scientists believe that increased cloud cover could also trap heat, leading to a greenhouse effect and global warming. The exact balance between cooling and warming effects depends on various factors, including the supernova's distance, intensity, and the planet's atmospheric composition. What we do know is that any rapid and drastic climate change can be devastating for life. Organisms adapted to specific temperature ranges and weather patterns may struggle to survive. Ecosystems can collapse as species migrate or go extinct. Mass extinctions in Earth's history have often been linked to periods of rapid climate change. Now, let's talk about radiation poisoning. Supernovae release a torrent of high-energy particles, including gamma rays, X-rays, and cosmic rays. These particles can penetrate living tissues, damaging cells and DNA. The severity of radiation poisoning depends on the dose received. At high doses, radiation poisoning can cause acute radiation syndrome, characterized by nausea, vomiting, fatigue, and hair loss. In severe cases, it can lead to organ failure and death. Even at lower doses, radiation exposure can increase the risk of cancer and other long-term health problems. The Earth's magnetic field and atmosphere provide some protection against cosmic radiation. However, a nearby supernova could overwhelm these defenses. Organisms living near the surface of the Earth would be particularly vulnerable. Marine life in shallow waters would also be at risk. Consider the impact on the food chain. If plants and animals are contaminated with radioactive isotopes, these isotopes can accumulate in the bodies of organisms that eat them. This process, known as biomagnification, can lead to even higher concentrations of radiation in top predators. What about atmospheric chemistry changes? A supernova's radiation can trigger a cascade of chemical reactions in the atmosphere, altering its composition. For example, nitrogen oxides produced by gamma rays can react with ozone, further depleting the ozone layer. The increased ionization of the atmosphere by cosmic rays can also affect cloud formation and precipitation patterns. Changes in atmospheric chemistry can have far-reaching consequences for ecosystems and human health. Acid rain, smog, and other forms of pollution can become more prevalent. But how do these potential supernova-induced disasters compare to known extinction events in Earth's history? Let's some examples. The Ordovician Silurian extinction event, which occurred about 443 million years ago, is one of the largest mass extinctions in Earth's history. Scientists believe that it may have been triggered by a gamma ray burst from a distant supernova. The evidence? A pulse of radiation could have depleted the ozone layer, leading to increased UV radiation and a global cooling event. The late Devonian extinction, which occurred about 375 million years ago, was another major extinction event. Several theories have been proposed to explain this extinction, including asteroid impacts, volcanic eruptions, and climate change. However, some scientists have suggested that a nearby supernova could have played a role. The Permian-Triassic extinction event, also known as the Great Dying, was the largest mass extinction in Earth's history. About 96% of marine species and 70% of terrestrial vertebrate species went extinct. The cause of this extinction is still debated, but volcanic activity, climate change, and asteroid impacts are all possibilities. Could a supernova have contributed to this catastrophe? It's certainly within the realm of possibility. These ancient extinction events provide a sobering reminder of the potential for cosmic events to reshape life on Earth. While we can't say for sure whether supernovae were directly responsible for these extinctions, the evidence suggests that they could have played a significant role. The key takeaway is this: a nearby supernova is not just a spectacular light show, it's a potential existential threat. The radiation, cosmic rays, and atmospheric changes triggered by a supernova could devastate ecosystems, disrupt the climate, and lead to mass extinctions. So, what can we do? Can we prepare for a supernova? Can we protect ourselves? Perhaps. But first, we need to know which stars in our neighborhood pose the greatest threat. Which stellar suspects are ticking time bombs, ready to explode and unleash their fury upon our planet? That's exactly what we'll be exploring in the next chapter. We'll take a comprehensive survey of known supernova candidates within threatening distance of Earth, including Betelgeuse, Wolf-Rayet stars, and other potential stellar time bombs. We'll analyze their current states and estimated timelines for explosion. You might be surprised by what we find. Chapter 5: Stellar Suspects in Our Neighborhood. Comprehensive survey of known supernova candidates within threatening distance of Earth, including Betelgeuse, Wolf-Rayet stars, and other potential stellar time bombs. Analyzes their current states and estimated timelines for explosion. Imagine living next door to a ticking time bomb. Not a literal one, of course, but something far more massive, far more powerful, and ultimately far more destructive. You might not even know it's there, quietly simmering, patiently waiting to unleash its fury upon the cosmos. Well, in a cosmic sense, we live next door to several of these potential doomsday devices. They're stars, and they're close enough that their eventual demise could have profound consequences for life on Earth. We've talked about the science, the theory, the terrifying potential of supernovae. Now, let's get personal. Let's look at some of the actual stars in our galactic neighborhood that are on the short list of cosmic killers. These aren't hypothetical threats. These are real, observable objects, each with its own unique characteristics and its own estimated countdown clock. First on our list, and probably the most famous, is Betelgeuse. A red supergiant star located in the constellation Orion, Betelgeuse is a true behemoth. If it were to replace our Sun, its surface would extend out past the orbit of Jupiter. That's a mind-boggling scale. For a while there, astronomers thought Betelgeuse about to explode. It experienced a dramatic dimming event, leading to speculation that it was shedding material in preparation for its final act. The internet was buzzing with supernova predictions, and the world held its breath. Ultimately, it turned out to be a less dramatic event, likely caused by a cloud of dust ejected from the star. But the scare served as a stark reminder. Betelgeuse explodes someday. It's nearing the end of its life, having burned through its supply of hydrogen fuel. Now, it's fusing heavier elements in its core, a process that can't continue indefinitely. So, when will Betelgeuse go supernova? That's the million-dollar question, isn't it? The truth is, we don't know for sure. It could be tomorrow. It could be a million years from now. Red supergiants like Betelgeuse are notoriously unpredictable. However, the general consensus is that it's likely to happen within the next 100 0000s. Now, 100 0000s might seem like a long time, but in cosmic terms, it's the blink of an eye. And at a distance of roughly 650 light-years, Betelgeuse is close enough that its supernova could have noticeable effects on Earth. The initial burst of radiation would be intense, potentially disrupting our atmosphere and affecting our climate. It wouldn't be an extinction-level event, but it would certainly be a significant event. But Betelgeuse isn't the only stellar suspect in our neighborhood. There are other stars that, while perhaps less well-known, pose a similar or even greater threat. Take the Wolf-Rayet stars, for example. These are hot, massive, and incredibly luminous stars that are rapidly shedding their outer layers through powerful stellar winds. They're essentially stars on steroids, burning through their fuel at an astonishing rate. One particularly interesting Wolf-Rayet star is WR104. Located about 8 WZ light-years away, WR1004 is a binary system, consisting of a Wolf-Rayet star and a companion star orbiting each other. What makes WR1004 particularly intriguing and somewhat alarming is its orientation. The system is orientation in such a way that if the Wolf-Rayet star were to explode as a supernova, the resulting gamma-ray burst could be directed towards Earth. Now, gamma-ray bursts are the most powerful explosions in the universe. They're incredibly focused beams of energy that can travel vast distances. If a gamma-ray burst from WR1004 were to hit Earth, it could have catastrophic consequences. It could strip away our ozone layer, exposing us to harmful ultraviolet radiation from the sun. It could also trigger significant climate change and potentially lead to a mass extinction event. The good news is that WR1004 is relatively far away, and there's some uncertainty about the exact orientation of the system. But the possibility of a gamma-ray burst hitting Earth from WR24 is certainly something that astronomers are taking seriously. Another potential supernova candidate is the star Ik Pegasi b. This is a white dwarf star that is part of a binary system with a normal star. The white dwarf is gradually pulling matter from its companion star, increasing its mass. If the white dwarf reaches a critical mass, known as the Chandrasekhar limit, it will explode as a Type Ia supernova. Type Ia supernovae are incredibly bright and uniform explosions, which makes them useful as standard candles for measuring distances in the universe. But they're also incredibly destructive. If Ik Pegasi b were to explode, it would release a tremendous amount of energy, potentially affecting nearby planetary systems. Fortunately, Ik Pegasi b is located about 150 light-years away, which is relatively close in cosmic terms, but probably not close enough to pose an immediate threat to Earth. However, it does serve as a reminder that even seemingly innocuous white dwarf stars can become cosmic bombs under the right circumstances. Then there are the blue supergiants, like Rigel in the constellation Orion. These stars are even more massive and luminous than red supergiants, and they have even shorter lifespans. They burn through their fuel at an incredibly rapid rate, and they're destined to end their lives as supernovae. While Rigel is much further away than Betelgeuse, roughly 860 light-years distant, there are other blue supergiants closer to us. These stars are constantly monitored by astronomers, searching for any signs of impending doom. Now, you might be thinking, this is all pretty scary. Are we just sitting ducks, waiting for one of these stars to explode and wipe us out? Well, the answer is both yes and no. Yes, we are vulnerable to the effects of supernovae. They are a natural part of the universe, and there's nothing we can do to stop them from happening. But no, we're not necessarily doomed. The universe is vast, and the odds of a supernova exploding close enough to Earth to cause an extinction-level event are relatively low. However, that doesn't mean we should ignore the threat. By studying these potential supernova candidates, by understanding the physics of stellar explosions, and by monitoring the skies for any signs of impending doom, we can better assess the risks and potentially develop strategies to mitigate the effects of a nearby supernova. It's important to remember that supernovae are not just destructive events. They also play a crucial role in the evolution of the universe. They are the primary source of heavy elements, the elements that make up our planet, our bodies, and everything around us. Without supernovae, there would be no carbon, no oxygen, no iron. We wouldn't be here. So, supernovae are both a threat and a gift. They are a reminder of the power and the violence of the universe, but they are also a testament to its creativity and its ability to create something new from the ashes of the old. The stars we've discussed are just a few of the many potential supernova candidates in our galactic neighborhood. There are likely many more that we haven't even discovered yet. And as our telescopes become more powerful and our understanding of stellar evolution deepens, we'll undoubtedly uncover even more potential threats, and perhaps even learn how to predict these events with greater accuracy. Understanding these stellar neighbors, their life cycles, and their potential for destruction is paramount. It's not just about fear, it's about knowledge, preparation, and ultimately, survival. We must continue to look up, to study the stars, and to learn everything we can about these cosmic time bombs that surround us. But simply identifying the suspects isn't enough. We need to understand how these explosions could actually impact our planet. What are the specific mechanisms by which a supernova could damage or destroy life on Earth? And how do these potential impacts compare to known extinction events in Earth's history? That's exactly what we'll explore next, as we delve into the weapons of mass extinction that supernovae wield. Chapter 6: Echoes from Ancient Explosions investigates historical evidence of past supernovae affecting Earth, including geological isotope signatures, fossil records of extinction events, and astronomical observations throughout human history. Explores what these past events teach us about supernova impacts. Imagine Earth as a detective, meticulously collecting clues from the scenes of ancient cosmic crimes. Supernovae, though distant and long past, leave behind fingerprints in our planet's geology, biology, and even in the records of human history. These aren't always obvious, screaming headlines. Sometimes they're subtle whispers, faint echoes that require careful listening to decipher. For decades, scientists have been piecing together this cosmic puzzle, searching for evidence that supernovae have indeed impacted our planet, and more importantly, what those impacts looked like. The story they're uncovering is both fascinating and a little unsettling. One of the most compelling lines of evidence comes from the realm of isotopes. Isotopes are variations of elements, differing in the number of neutrons they possess. Some isotopes are stable, while others are radioactive, decaying at predictable rates. When a supernova erupts, it forges elements in its fiery heart, including some very specific radioactive isotopes that are quite rare on Earth. Think of it like this. If you find a particular brand of rare foreign coin scattered across a beach, you might reasonably suspect a shipwreck. Similarly, the discovery of unusual isotopes in Earth's geological layers can point to a supernova event. One isotope that has garnered significant attention is iron-60. Iron-60 is radioactive, with a half-life of about 6 million years. This means that after 6 million years, half of a given sample of iron-60 will have decayed into other elements. Because of its relatively short lifespan in geological terms, any iron-60 found on Earth must have been deposited relatively recently, astronomically speaking, of course. So where do we find this iron-60? Well, scientists have discovered it in deep-sea sediments, in lunar samples, and even in ancient bacterial fossils. The concentration of iron-60 in these layers shows a distinct peak, suggesting a spike in its deposition around 2 to 3 million years ago. This is a crucial piece of the puzzle. But how could this iron-60 reach Earth? Supernovae eject vast amounts of material into space, including these newly forged isotopes. As the supernova remnant expands, it can interact with the interstellar medium, accelerating particles to incredibly high speeds. These particles, including iron-60, can then travel across interstellar distances and eventually reach our solar system, raining down on Earth. The discovery of iron-60 provides strong evidence that a supernova explosion occurred relatively close to our solar system a few million years ago. But how close is close? And what effects might it have had on Earth? That's where things get even more interesting. Another fascinating piece of evidence comes from the study of beryllium-10. Beryllium-10 is another radioactive isotope, but unlike iron-60, it's not directly produced in supernovae. Instead, it's created when cosmic rays bombard the atmosphere. Now, remember how supernovae can accelerate particles to incredibly high speeds. These particles become cosmic rays, bombarding everything in their path. An increase in cosmic ray flux would lead to an increase in the production of beryllium-10 in Earth's atmosphere, which would then be deposited in ice cores and sediments. Studies of ice cores and sediment layers have revealed a peak in beryllium-10 concentrations around the same time as the iron-60 spike, further supporting the idea of a nearby supernova event. It's like finding two different types of evidence pointing to the same crime scene. The isotopes act like cosmic clues, leading us back to a supernova that exploded in our galactic neighborhood. But the evidence isn't just limited to isotopes. The fossil record, too, holds potential clues about past supernova impacts. While it's difficult to directly link specific extinction events to supernovae, some researchers have proposed a connection between supernova activity and periods of significant biodiversity loss. One such event is the Pliocene-Pleistocene boundary, around 6 million years ago. This period saw significant changes in Earth's climate, with the onset of the ice ages. Some scientists have suggested that a nearby supernova could have contributed to these climate changes by increasing cloud cover and altering atmospheric chemistry. It's important to emphasize that the link between supernovae and extinction events is still a matter of debate. The fossil record is complex, and many factors can contribute to biodiversity loss. However, the possibility that supernovae have played a role in shaping the history of life on Earth is a compelling one. Imagine the effects of a supernova on our atmosphere. A surge of radiation could deplete the ozone layer, leaving life on Earth more vulnerable to harmful ultraviolet radiation from the sun. Changes in atmospheric chemistry could lead to acid rain and other environmental disruptions. And, as we discussed earlier, an increase in cosmic rays could increase mutation rates, potentially accelerating evolutionary change. These are just some of the ways that a supernova could impact life on Earth. While a single supernova might not be enough to cause a mass extinction, a series of supernovae over time could potentially have a cumulative effect, shaping the course of evolution. Beyond the geological and biological evidence, there's another fascinating source of information: historical astronomical observations. For centuries, humans have gazed at the night sky, recording their observations of celestial events. While ancient astronomers didn't understand supernovae in the way we do today, they did observe bright new stars that suddenly appeared in the heavens. The most famous example is the supernova of 1054 AD, which created the Crab Nebula. This event was recorded by Chinese astronomers who described it as a guest star that was visible even during the day for several weeks. While the 1054 supernova was relatively distant, it serves as a reminder that supernovae are not just theoretical events. They are real, observable phenomena that have been witnessed by humans throughout history. Could other, less well-documented supernovae have occurred closer to Earth, leaving a more significant impact? It's a question that continues to drive research. Astronomers are constantly searching historical records for mentions of unusual celestial events that might correspond to previously unknown supernovae. These records, often found in ancient texts and forgotten manuscripts, can provide valuable insights into the frequency and distribution of supernovae in our galaxy. Think about it. A dedicated monk meticulously documenting a bright new star in the year 800 AD, unaware that he's recording a potentially life-altering event for his planet. These historical observations offer a unique window into the past, allowing us to piece together a more complete picture of supernova activity in our cosmic neighborhood. The challenge, of course, is to distinguish between genuine supernova observations and other celestial phenomena, such as comets or novae. This requires careful analysis of historical records, taking into account the limitations of ancient astronomical techniques and the cultural context in which the observations were made. Despite these challenges, the search for historical supernova records continues to be a fruitful area of research. Each new discovery brings us closer to understanding the true impact of supernovae on Earth's history. So, what can we conclude from all this evidence? The geological record, the fossil record, and historical astronomical observations all suggest that supernovae have indeed impacted Earth in the past. While the exact nature and extent of these impacts are still being investigated, the evidence is compelling. We know that supernovae can deposit radioactive isotopes on Earth, increase cosmic ray flux, and potentially disrupt the atmosphere. We also know that supernovae have been observed throughout human history, reminding us that these events are a real and ongoing part of our cosmic environment. The story of supernovae and their impact on Earth is a complex and evolving one. It requires a multidisciplinary approach, bringing together expertise from astronomy, geology, biology, and history. As we continue to gather more evidence, we'll gain a deeper understanding of the role that supernovae have played in shaping our planet and the life it supports. But this raises a critical question. If supernovae have impacted Earth in the past, what about the future? Are there any potential supernova candidates in our neighborhood that could pose a threat to our planet? What are scientists doing to monitor these potential threats and prepare for the possibility of a nearby supernova explosion? But this discovery was only the beginning, because next we uncover the list of stellar suspects lurking in our cosmic neighborhood, stars that could potentially go supernova and send a deadly wave of radiation towards Earth. You might be surprised by what astronomers have already identified, and how close some of these potential threats really are. I hope you're as amazed by this as I am. If you want to stay updated on more content like this, make sure to subscribe and join our community of curious minds. Trust me, what's coming next will challenge everything you thought you knew. Chapter 7. Monitoring the Cosmic Threat examines current astronomical surveillance efforts to detect and monitor potential supernova threats, including space-based telescopes, early warning systems, and the challenges of predicting stellar explosions. Discusses the timeline between detection and impact. The universe, as we've seen, is a dangerous place. And while we might feel safe nestled here on Earth, orbiting our sun, cosmic threats lurk. Supernovae are among the most spectacular and potentially devastating of these threats. But are we just sitting ducks, waiting for a stellar explosion to wipe us out? Or are we actively watching the skies, preparing for the worst? The good news is we're not completely blind. Astronomers around the world are engaged in a constant vigil, scanning the heavens for signs of impending cosmic doom. It's a complex and challenging task, akin to searching for a needle in a cosmic haystack. But the stakes are incredibly high. So how exactly do we go about monitoring the cosmic threat of supernovae? What tools and techniques do we use, and how much warning would we actually get? Our primary defense against the unknown is, of course, observation. Telescopes, both on Earth and in space, are our eyes on the universe. They allow us to peer into the distant reaches of space, gathering light and information from stars and galaxies. Space-based telescopes, like the Hubble Space Telescope, offer a particularly clear view, unburdened by the Earth's atmosphere. They can observe in wavelengths of light that are blocked by our atmosphere, providing valuable insights into the processes occurring within stars. Hubble, for example, has been instrumental in studying the progenitors of supernovae, the stars that eventually explode. By analyzing their properties before they detonate, we can learn more about the conditions that lead to these cataclysmic events. Then there's the James Webb Space Telescope, Hubble's successor. Webb is even more powerful, capable of seeing deeper into space and observing in infrared light, which allows it to penetrate through dust clouds and reveal hidden stellar nurseries and dying stars. Webb is already providing unprecedented views of the universe, and it promises to revolutionize our understanding of supernovae and their potential impact on Earth. What secrets will it unlock about the stars that might threaten our existence? On the ground, massive telescopes like the Very Large Telescope in Chile and the Keck Observatory in Hawaii are also playing a crucial role. These telescopes use advanced techniques like adaptive optics to compensate for the blurring effects of the atmosphere, allowing them to achieve remarkably sharp images. They are also equipped with spectrographs, instruments that can analyze the light from stars and determine their chemical composition, temperature, and velocity. This information can help us identify stars that are nearing the end of their lives and are likely to explode as supernovae. But simply observing stars isn't enough. We need to be able to detect changes in their brightness and behavior that might indicate an impending explosion. This is where astronomical surveys come in. These surveys systematically scan large areas of the sky, looking for transient events, things that appear and disappear over time. Supernovae, of course, are prime targets for these surveys. One of the most successful supernova surveys is the All-Sky Automated Survey for Supernovae, or ASAS-SN. This project uses a network of small, relatively inexpensive telescopes located around the world to monitor the entire sky every few days. When a new supernova is detected, ASAS-SN alerts astronomers, who can then follow up with larger telescopes to study the event in more detail. Another important survey is the Zwicky Transient Facility, or ZTF, which uses a powerful camera on the Samuel Oschin telescope at Palomar Observatory to scan the sky for transient events. ZTF is particularly good at finding supernovae in their early stages, which is crucial for understanding the explosion mechanism. These surveys are generating a vast amount of data, far more than any human could possibly analyze. This is where machine learning and artificial intelligence come in. Algorithms can be trained to identify supernovae in the data, even if they are faint or obscured by dust. These algorithms can also be used to predict when and where supernovae are likely to occur, based on the properties of the stars in a given region of the sky. However, predicting stellar explosions is an incredibly complex task. Stars are governed by a complex interplay of physical processes, and even small changes in their internal conditions can have dramatic effects on their evolution. We can model these processes using powerful computers, but our models are still imperfect. One of the biggest challenges is understanding the late stages of stellar evolution, the period just before a star explodes. This is when the star's core is undergoing rapid changes, and the processes that lead to the explosion are highly sensitive to the initial conditions. We need to observe more stars in these late stages of evolution to improve our models and make more accurate predictions. Even if we can't predict exactly when a star will explode, we can still estimate the likelihood of a supernova occurring in a given region of the sky. By analyzing the types of stars that are present and their distances from Earth, we can assess the overall supernova risk. This information can be used to prioritize our monitoring efforts and focus on the regions of the sky that are most likely to produce a supernova that could affect Earth. But let's say we do detect a star that is about to explode as a supernova. How much warning would we actually get? The answer depends on several factors, including the distance to the star and the type of supernova. For a Type II supernova, which results from the core collapse of a massive star, we might get a few days' warning. As the star's core collapses, it emits a burst of neutrinos, tiny subatomic particles that can travel through matter virtually unimpeded. These neutrinos can be detected by underground detectors, like the Super Kamiokande detector in Japan. The detection of a neutrino burst would be an early warning sign that a supernova is imminent. After the neutrino burst, we would see a rapid increase in the star's brightness as the shock wave from the core collapse reaches the surface. This brightening can be detected by telescopes around the world, providing further confirmation that a supernova is about to occur. For a Type Ia supernova, which results from the explosion of a white dwarf star, the warning time is much shorter. These supernovae are thought to be triggered by the white dwarf accreting matter from a companion star. When the white dwarf reaches a critical mass, it ignites a runaway nuclear reaction that destroys the star in a matter of seconds. Because the explosion is so rapid, there is very little warning. We might see a slight increase in the white dwarf's brightness in the days or weeks leading up to the explosion, but this would be very difficult to detect. In most cases, we would only know that a Type Ia supernova had occurred after it had already happened. So, what happens after we detect a supernova? What are the immediate steps that we would take to assess the threat to Earth? The first step would be to determine the distance to the supernova. This can be done by measuring the supernova's brightness and comparing it to the expected brightness for that type of supernova. The fainter the supernova, the farther away it is. Once we know the distance, we can calculate the amount of energy that is being released by the supernova. This will give us an idea of the potential impact on Earth. We would also want to determine the type of supernova. Type II supernovae are generally less energetic than Type Ia supernovae, but they can still pose a significant threat if they are close enough. Finally, we would want to analyze the spectrum of the supernova. This will tell us the chemical composition of the material that is being ejected from the star. This information can be used to assess the potential for the supernova to produce harmful radiation, like gamma rays and X-rays. All of this data would be fed into computer models to simulate the effects of the supernova on Earth. These models would take into account the distance to the supernova, the type of supernova, the amount of energy being released, and the chemical composition of the ejected material. The models would then predict the impact on Earth's atmosphere, climate, and biosphere. The results of these simulations would be used to inform decisions about whether to take any protective measures. These measures could include evacuating vulnerable populations, shielding sensitive equipment, and developing strategies to mitigate the long-term effects of the supernova. The timeline between detection and impact is, as you can imagine, crucial. A few days' warning might be enough to take some protective measures, but it wouldn't be enough to completely eliminate the risk. A few weeks or months' warning would give us more time to prepare, but even then the challenges would be immense. The biggest challenge is the uncertainty in our predictions. We can never be completely sure of the distance to a supernova, the type of supernova, or the amount of energy being released. This means that our simulations will always have some degree of uncertainty. This uncertainty makes it difficult to make informed decisions about what protective measures to take. If we overestimate the threat, we might take unnecessary precautions that disrupt our lives and economies. If we underestimate the threat, we might not take enough precautions and suffer the consequences. Despite these challenges, our ability to monitor the cosmic threat of supernovae is constantly improving. New telescopes, new surveys, and new algorithms are being developed all the time. We are learning more about the lives and deaths of stars, and we are getting better at predicting when and where supernovae are likely to occur. This knowledge is essential for protecting ourselves from the potentially devastating effects of these cosmic explosions. It's a race against time, a race to understand the universe before it throws another curveball our way. And while the odds may seem daunting, the pursuit of knowledge, the drive to understand our place in the cosmos, is a reward in itself. But what if, despite all our monitoring efforts, a supernova were to occur close enough to Earth to pose a serious threat? What options would we have? Could we actually survive a nearby supernova? That's what we'll explore next, as we delve into the potential strategies for surviving the stellar apocalypse. Chapter 8. Surviving the Stellar Apocalypse explores potential human responses to an imminent nearby supernova, from technological solutions to species survival strategies. Concludes with reflection on humanity's place in a universe where such cosmic catastrophes are inevitable, and what this means for our long-term future as a species. Okay, so, a nearby supernova. We've established the threat, the mechanisms, and even identified a few potential culprits lurking in our cosmic neighborhood. But what if the unthinkable happens? What if the early warning systems blare, the data confirms it, and we know with chilling certainty that a stellar explosion is headed our way? What then? The honest answer is, there are no easy solutions, no magic shields we can raise, no simple button we can push to make it all go away. But that doesn't mean we're entirely helpless. Human ingenuity, driven by the primal urge to survive, might just offer a few glimmers of hope. Let's start with the technological possibilities. Could we perhaps deflect the worst of the radiation? It sounds like science fiction, I know. But think about it. We're already developing technologies to deflect asteroids, to nudge them off potentially catastrophic collision courses. Could a similar principle be applied, on a much grander scale, to the radiation emanating from a supernova? One theoretical approach involves creating a massive magnetic field, a sort of planetary-scale shield, to deflect charged particles. This would require an absolutely enormous amount of energy, and a network of superconducting cables stretching across a significant portion of the Earth's surface. The logistical challenges are staggering, to say the least. But if the alternative is planetary devastation, perhaps such a massive undertaking becomes justifiable. Another, even more ambitious idea involves using advanced laser technology to vaporize or deflect some of the incoming radiation. This would require a network of incredibly powerful lasers, positioned in space, constantly firing at the approaching wave of energy. The energy requirements would be astronomical, and the potential for unforeseen consequences, for example, accidentally focusing the radiation intensely on a specific area, would be immense. These are, admittedly, long shots. They're based on technologies that are still in their infancy, and they would require a level of global cooperation and resource allocation that we've never achieved before. But the point is, we're not entirely without options. Faced with an existential threat, humanity has a remarkable capacity for innovation. But what if these technological solutions prove to be beyond our reach? What if the supernova is simply too powerful, too close, and too fast for us to effectively mitigate its effects? Then we have to consider strategies for survival, for preserving the human species in the face of near-certain catastrophe. One possibility, a rather grim one, is to seek refuge deep underground. Bunkers, mines, even specially designed subterranean cities could offer some protection from the initial blast of radiation and the subsequent environmental fallout. The deeper you go, the more shielding you have. The challenge, of course, is that these underground shelters would need to be completely self-sufficient, capable of providing food, water, and energy for decades, perhaps even centuries. Imagine a world where the surface is uninhabitable, poisoned by radiation and choked with dust. The only survivors are those who manage to burrow deep into the earth, living in artificial ecosystems, cut off from the sun and the sky. It's a bleak picture, but it might be the only way to ensure the survival of at least a portion of humanity. Another, more ambitious survival strategy involves leaving the planet altogether. Could we build a fleet of interstellar arks capable of carrying a representative sample of humanity and the seeds of our civilization to another star system? This is the ultimate escape plan, the cosmic lifeboat. The challenges, of course, are immense. We don't currently have the technology to travel to another star system within a reasonable time frame. Even with advanced propulsion systems, the journey would take generations, perhaps even centuries. And then there's the question of where to go. Finding a habitable planet, one that's capable of supporting human life, is no easy task. But, again, the possibility is there. We're already exploring the solar system, searching for potentially habitable worlds. We're developing advanced propulsion systems, like fusion rockets and warp drives, that could one day make interstellar travel a reality. And we're learning more and more about the universe around us, discovering new planets and new possibilities every day. Perhaps, in the face of a supernova threat, we could accelerate these efforts, pouring all of our resources into building a fleet of interstellar arks and sending them out into the galaxy in search of a new home. It would be a long shot, a desperate gamble. But it might be our only chance to ensure the long-term survival of the human species. Of course, even if we manage to survive, either through technological mitigation or through escape, the world that emerges on the other side of the supernova will be profoundly different. The Earth, even if it remains habitable, will be scarred and changed. The survivors, whether they're living in underground bunkers or on a distant planet, will have to rebuild civilization from scratch. And that raises a fundamental question. What kind of civilization do we want to rebuild? What lessons will we have learned from the experience of facing near extinction? Will we be more cooperative, more sustainable, more focused on the long-term survival of our species? Or will we simply repeat the mistakes of the past, setting ourselves up for another potential catastrophe in the future? The answer, I think, lies in our ability to learn from the past, to understand our place in the universe, and to act accordingly. We are, after all, a relatively young species, still learning the ropes of cosmic survival. We've made mistakes, we've taken wrong turns, but we've also shown an incredible capacity for resilience and adaptation. And that's what gives me hope, even in the face of a threat as daunting as a nearby supernova. The human spirit, the drive to survive, the thirst for knowledge, these are powerful forces. And they may just be enough to carry us through, to help us navigate the cosmic storms and emerge, stronger and wiser, on the other side. But let's be clear, survival isn't just about technology or grand escape plans. It's also about the choices we make right now. It's about investing in scientific research, about fostering global cooperation, about promoting sustainable practices, and about educating future generations about the threats and opportunities that lie ahead. It's about recognizing that we are all interconnected, that our fate is intertwined with the fate of the planet and with the fate of the universe. And it's about acting accordingly, making choices that benefit not just ourselves, but all of humanity and all of life on Earth. Ultimately, the question of how we survive a supernova is a question of how we choose to live our lives. Do we live in a way that makes us vulnerable, that exposes us to unnecessary risks? Or do we live in a way that makes us resilient, that prepares us for the challenges that lie ahead? The answer, I believe, is clear. We must choose to live in a way that promotes survival, not just for ourselves, but for all of humanity. We must invest in science, in education, in sustainability, and in global cooperation. We must recognize that we are all part of something larger than ourselves, and that our actions have consequences that extend far beyond our own lives. And finally, we must confront the existential reality that the universe is a dangerous place, filled with unpredictable events and potentially catastrophic forces. Supernovae are just one example of the many threats that we face. Asteroid impacts, climate change, pandemics. These are all potential extinction-level events that could wipe us off the face of the Earth. But that doesn't mean we should give up. It doesn't mean we should succumb to despair. It means we should be vigilant, we should be prepared, and we should do everything in our power to mitigate these risks. Because ultimately, the survival of humanity is not guaranteed. It's something we have to earn, something we have to fight for, and the choices we make today will determine whether we succeed or fail. So, what does all of this mean for our long-term future as a species? It means that we need to think differently, more strategically, and more collectively about our place in the cosmos. We need to recognize that we are not alone, that we are part of a vast and complex universe, filled with both wonder and peril. We need to embrace science, not fear it. We need to invest in research, not cut it. We need to educate our children about the threats and opportunities that lie ahead, so that they can make informed decisions about the future. And we need to work together, not against each other. Global cooperation is essential if we are to overcome the challenges that face us, whether it's a supernova, an asteroid impact, or climate change. The future is uncertain, but it's not predetermined. We have the power to shape our own destiny, to create a better world for ourselves and for future generations. But it requires us to act now, to make the right choices, and to work together towards a common goal. This brings us to a deeper understanding of our cosmic insignificance, doesn't it? The universe doesn't care about us. It doesn't have a plan for us. It's just a vast, indifferent expanse of space and time filled with countless stars and planets, galaxies and nebulae. And yet, here we are, a tiny speck of life on a tiny planet, contemplating the mysteries of the universe. We are, in a sense, a miracle. We are a testament to the power of life to emerge and evolve, even in the face of overwhelming odds. And that's something to celebrate. It's something to cherish. It's something to protect. Because we don't know if there's other life out there, other civilizations struggling to survive. We may be the only ones. And if that's the case, then it's all the more important that we take care of ourselves, that we protect our planet, and that we strive to create a better future for all of humanity. Because if we fail, then all of this, all of our hopes, our dreams, our achievements, will be lost. So, look up at the night sky, not with fear, but with awe and wonder. Remember that you are part of something extraordinary, something precious, something worth fighting for. And let that inspire you to make the world a better place, to protect our planet, and to ensure the survival of humanity for generations to come. The cosmic stage is set, and our role is yet to be fully written. We must choose wisely. But what if the echoes of these ancient explosions aren't just whispers from the past? What if they hold clues to predicting future events, to understanding the subtle warning signs that precede a supernova? And what if, buried within these geological records lies a secret code, a key to unlocking the mysteries of stellar death itself? That's exactly what we'll be exploring next, as we delve into the hidden history of our planet and the astronomical observations that have shaped our understanding of these cosmic events.